No, it's really good to be here today and kind of share with you kind of my thoughts, on chiplets. And certainly, I think in doing that is really, and probably this audience perhaps more than any other kind of understands the industry trends and driving forces, but I certainly want to give you kind of my thoughts on that and talk about that. Then I'll give you an example that's maybe not so fictional of the advantage of chiplets, unless it's lost on anybody. And then talk a little bit about the partnerships and really the Cadence approach in helping the industry. This is obviously a trend that is, I would say, center stage for us. And then a little summary. So I don't know how many are familiar with Amara's law, but it's how humans think about the future. It says we tend to overestimate the effect of a technology in the short run and underestimate the effect in the long run. And I certainly think this is applicable to the topic of chiplets in a very big way. We saw this clearly with the internet. I think we clearly see this, playing out with AI, and I think chiplets is no different. In the beginning, I think we've probably overestimated, kind of how fast we would get there and the impact. But I think long term, we are way underestimating the impact of chiplets in the industry and how it's going to kind of reshape design and really everything we do. Many of you are probably aware. So I remember I'm old. Been in 25 years or plus. Kind of designing chips and I remember actually my favorite node of all time was one called 860. It's where we moved to copper interconnects at that time and really we got a 30% bump just in performance from the interconnects and the transistor. Everything just scaled perfectly. And on top of that, we got about a 2x kind of area improvement. And so logic scaling, clearly, as we've seen over time now, has slowed pretty dramatically. And really, even more than logic scaling, memory scaling has slowed down even more so. And perhaps maybe with stacked CMOS, we'll get a kind of a one-time bump, here in the near future, potentially with memory scaling. But certainly analog scaling. So clearly the message is advanced node technology scaling has slowed down pretty dramatically. But the one thing that has not slowed down and has actually accelerated is the cost of silicon. And I think this is, I call it the problem of CPT. This is, CPT stands for cost per transistor. And if you look at it, and I've kind of abstracted the process nodes, but mainly just kind of focus generationally what's been happening. If you look at it, traditionally in terms of scaling from one, if you go back many years, you would roughly get about 0.6 from a scaling perspective. Certainly, the composition of chips varies wildly, but roughly about 0.6. And then the incremental wafer cost from generation to generation was roughly about 10%, maybe a little bit more. And what cost per transistor is very simple. You just multiply wafer cost by the expected scaling, kind of a feature neutral scaling, and you would roughly end up, it's around kind of, 0.7. 0.69 is really kind of was an industry average. And so it always made, and why this is so meaningful is it always made sense, almost always, to go to the next generation, right? Transistors were just cheaper. So now what you see is really the process technology is increasing. The wafer cost from one generation to the next is no longer 10 to 15%. It's much more than that. The scaling is less than that, so the cost per transistor is going up pretty dramatically. So the design complexity is increasing each generation, and this is really a massive first-order problem, in the industry. So none of this is to say you still need clearly let me go back one here, but you still need the power, the performance benefits of advanced node transistors. They're just simply far more expensive. And so you have to be far more judicious. It requires quite a bit, I would say, more design wisdom in how you use transistors given the incremental costs going forward. And we love to talk about Moore's Law. I was trained, I guess you could say, in the pantheon or the cathedral of Moore's Law. I spent many years at Intel. But I think now what is becoming as important or perhaps more important than Moore's Law is really the advances in packaging technology. If you look at just kind of 2D monolithic designs and kind of just traditional kind of 130 bump pitch. We've been doing MCP designs for a very, very long time. Then comes along 2.5D, with interposer, and really kind of the notion of chiplets begins to emerge. A few more choices also kind of come with that. Bump pitches, you're able to scale those down to 36, 46, and even down to maybe, I didn't put it on here, but you can get down to 25 and 18 micron bump pitches. And then really, with the advent of 3D chiplet designs, especially with hybrid bonding, where you actually have a roadmap now from the copper pillar interconnects, top to bottom die. Today 9 micron, roadmap for 6 micron, 3 micron, and eventually there's actually a roadmap down to a single micron bump pitch. And as you start to get down to, say, a single micron bump pitch, you can almost begin to think of, and I'll end my talk at the end with talking about this, but once you get bump pitches from a 3D standpoint that are in the kind of micron range, you can almost begin to think of designing the chiplets almost as if they were monolithic again in that context. So really, I would say packaging advancements are now, and I don't think it's wrong to say this, but it's almost more important than Moore's Law. And it's really interesting when you look at the foundries themselves. If you go look at what they're spending in terms of CapEx, process, and packaging, roughly they spend about 10% of their R&D on packaging technology versus process investment. That's roughly about the ratio. Really, I think you'll see that increase over time, where their CapEx and what they are spending will continue to go up. But it's interesting, with 3D and 2.5D, from an architecture standpoint, I can tell you a lot of the ideas and what we're doing now kind of in the architecture space, are ideas that we had 15, 20 years ago. We just simply could not do them because of the packaging technology limitations, and those barriers are largely gone. And it's really kind of an exciting time to be an architect in this time. And in terms of the industry trends that are driving growth in the semiconductor TAM, so we talked about disaggregation, and we talked about really just this notion of the cost of transistors and having to be far more judicious in how you use them. AMD with Ryzen, this is a great example. From an R&D and cost, and I'll walk you through an example and kind of give you kind of roughly how the costs kind of shift with that. But the ability to design your SoC, and then really as a new core comes out, to simply just design a new CPU core chiplet and be able to refresh your design and get to market. A dramatic reduction in time there. And also, if you look at just really, I had this, we talked about disaggregation, but I think one, I call it economy of scale. For me, it's I don't know how many people are from Google or Meta or Microsoft or Alibaba or Tencent in the room, but it is profound if you actually sit down and you look at how much money they actually spend in their data centers and their infrastructure. Typically we think of TSMC as probably the most capital-intensive company in the world. They spend roughly $34 billion a year. Some of these data center companies spend more than that on their own infrastructure. They have an economy of scale. They can no longer really afford to use commercial silicon. They have to go with really custom silicon. To really, power budgets are fixed in most of these data centers, yet the demand for performance continues to increase. Dark silicon is a real issue. You can no longer really afford dark silicon. How do you manage power? So really this, we talk about the semiconductor TAM, but we see this in the data center where there's need for custom silicon, but we also see, this notion of, when I talk about the number of advanced node design starts, we're seeing hyper segmentation, not only in enterprise and data center, but we're seeing hyper segmentation now. We're seeing it in automotive, which is really, I used to think of, kind of my old life, automotive is kind of, they would always lag in terms of kind of the state of the art, but now automotive quickly is one of the, I would say, more enthusiastic adopters of chiplets in kind of new architecture. But we see it in consumer and automotive, aerospace and defense, even, in terms of looking at their, the sheer number of advanced node design starts is pretty staggering, and that will continue to rise. And then, the design cost by node, and I say silicon solutions focus, and we'll talk a little bit here in a second about, abstraction levels. But really, you can no longer, you have to think in it with a solutions mindset to be able to maintain, manage costs, and just scale with the pace. And another one is foundry multi-sourcing. This is big too. This almost has kind of a geopolitical tint to it, but I think it also has a specialization bent to it. But you see, really, you see, Intel, getting into the foundry business. You see Samsung. You see, certainly Global Foundries. Obviously, the giant TSMC. You have, upstart, in Japan with Rapidus. You see this regional drive to have a global, assurance of a supply chain, and really, and I think what will be interesting, kind of as you get 10 years from now, is how do designers think about the different foundries and looking at their designs, and how do they plan for the technologies that are available there. But certainly, design companies looking to multi-source. There's even a geopolitical need for that, and so again, the semiconductor TAM is growing almost unbounded. Okay, so an example, just a simple example. This is, I would say it's not necessarily, it's not a fictional one, but you take your traditional monolithic SoC that has, say, a consumer SoC that has everything that you need on it in terms of all of the I/O, NPU, GPU, media display, all of the fabrics that are needed, and as you disaggregate it, there's many different choices you can make. As you create your substrate, and one that's very popular is you can take your CPU cores and cache and create that as a separate chiplet, a separate subsystem altogether. Graphics, yet another. The rest of the SoC that may have all of your other kind of IP agents, and then you can have a separate kind of I/O tile. This is one way to partition, say, a consumer related SoC. And in each one of these nodes, and we'll talk a little bit here in a second, is you have selected a process node that has the transistor that is kind of optimized for the workload and the function that you're trying to achieve here. And what's great is once you actually make this transition, say, from the monolithic to the chiplet space, from a business standpoint, let's say you come out with you can now kind of unlock, and you no longer have to gear the development of your GPU with your CPU, with your I/O, with kind of your media or NPU or VPU units. And if you have a new CPU coming out, you can refresh that new CPU either on a new process or a new architecture, or you can do both. And this can actually fit right into your existing platform, your existing socket, and you didn't have to redesign your graphics, the rest of your SoC or the I/O chiplet. And again, you can get even more radical. Let's say, yet again, another CPU generation comes out, and then a new graphics generation comes out, and you're able to, again, this leverage becomes tremendous in this context. So what is this? This, like I said, this is not a theoretical example. And if you want to kind of understand the impact on cost, both I would say from a CapEx and an OpEx standpoint, I think, and now having worked with many design companies, I think always that initial transition, say, from a monolithic to a chiplet-based architecture, they discover it's about the same amount of effort as designing the monolithic design as moving to the chiplet-based design in that first generation. But because of the increasing cost of silicon, they're able to better optimize the product cost. And so the actual product cost begins to go down, and then the R&D costs become tremendous as you get to the second generation and you get to the third generation. You're no longer having to do a second, third, and fourth complete monolithic redesign of the CPU, and you'll be able to leverage now engineering costs as well as, say, silicon costs. And then the ability to actually, I talked about segmentation. There's hyper-segmentation in all of these different markets that are going on right now, and that puts tremendous pressure on companies and in their verticals to be able to offer customers and consumers what they need. And they now have a tool in their toolbox to be able to generate the segments and to segment at much lower cost. So the number of products that they can actually produce and release goes up. So this is kind of high level, kind of the business, kind of aspect, in a world of kind of increasing silicon cost. These are the benefits that you actually see with chiplets. So the advantage of chiplets is probably not lost on anybody in here when I say disaggregated design, but clearly, as I just showed you, modularity is key. You have an ability now to create very complex systems with pre-designed, pre-verified chiplets instead of monolithic chips. The ability to even just leverage your verification collateral from one generation to the next should not be understated. This is probably, I would say, almost the biggest design challenge that many companies have. That in and of itself is tremendous. Customization, the ability to combine different chiplets in various configurations, to meet specific power, performance, and cost needs. I call this the right transistor for the right job on the right process node. And another one here is improved yield. And I think this is probably not well understood by most, but this is perhaps the most profound. Clearly, as you get, larger die sizes, and really, one of the things with chiplets, we keep bumping up against many, against the reticle size, a 33 by 25, and the need of AI demands even, much greater than that. So essentially, what we actually want to do in our designs is outpacing kind of what we can actually fit inside a reticle. And really, a full chip reticle modern, node does not yield very well. And as you move and you kind of move to a disaggregated architecture, clearly, as if you know anything about yield, your yield goes up. It's not linear. Okay, it's it really will go up. It's kind of a square function. So combining different, this is really important. And I think that unless you have almost, I can tell you, boy, I wish, in terms of full reticle die size, right, you have to have almost a perfectly yielding wafer to justify that anymore on an advanced node, and those simply don't exist. And so really disaggregating and going to a chiplet architecture is really absolutely needed on advanced nodes. So improved PPA, again, this is obvious, fitting the right IP to the right process node. Also with advanced nodes, what you see is digital logic may mature quickly, but another major component to this is just variation. And it takes a lot longer now on advanced nodes for that variation to tighten. And the amount of effort that goes into the analog mixed signal design on advanced nodes and dealing with variation. So really sometimes it makes sense to have your analog mixed signal nodes on an N-1 node simply because that node is mature. So the ability with chiplets and disaggregation now to allow advanced nodes to take advantage of kind of the power performance of digital transistors and allow an N-1 mature node where the variation is now tight is easier to design your analog circuits on. Now, and also improved scalability. New chiplets, developed, integrated into existing designs, as I say here, to improve performance. You can add features without redesigning the entire chip. So, the advantages are great. And so ChatGPT, what is a chiplet? I won't read it here. You can read through it quickly. So there's enough said about this on the internet that the definition is, what ChatGPT spits out is probably what most of you would spit out, right? So there's, it's well into the mind of the community what a chiplet is. I like to think about chiplets also in another way is we look at traditional abstract layers to handle complexity, right? This is the way this is the way all of us operate, right? We need different layers of abstraction to be able to handle complexity. I'm old enough where I go back where I hand drew everything. And literally, not only would we hand draw, kind of transistors and logic gates, we would actually even do a lot of the layout by hand. And then along come, standard cells, right? Different layers of abstraction to kind of help deal with the scaling complexity of Moore's Law with software stacks. But this is just, the way we operate, and this is the way we design products. I think chiplets, another way to think about them is they offer a much needed level of new layer of abstraction. And I think you talk about what chiplet will I buy tomorrow. I guess that's the theme already for next year. Think about it, in a way, if that world actually emerges and really does exist, that is really another way to think about that is you're able to buy a layer of abstraction that, where you no longer have to develop the microarchitecture, you no longer have to, to validate this from an electrical, physical, software standpoint. you are now able to design at the chiplet level. So we come a long way, but chiplets, I think, whether you put it in as kind of a new layer of abstraction, but eventually, I think a great way to think about this, chiplets offer a new design layer of abstraction. And I think this is, chiplet, it's one of those things where now you have a tool that enables you to solve many of the problems, but fundamentally we still, I think EDA, and I think one of the things that was exciting to me about coming to Cadence is I spent 26 years of my life kind of developing products. Being able to come to Cadence, for me was a unique. I could sit kind of at this nexus of the R&D EDA teams, bring kind of a product mindset, and then looking at kind of the advent of what is going on kind of in chiplets and where the market is moving itself, and then how do you bring a level of design automation to this that can actually add yet another layer of abstraction almost in helping things. I mean, from design teams, right? We say here, David Glasgow, who works with me, put this together, but challenged with many, from design specification to performance modeling to IP selection to implementation, verification, software, all of these many different tasks. And I didn't put in here, packaging, itself. Dealing with, packaging is another major task, kind of in the whole design flow. And if you happen to know the corpus of your IP, if you happen to know not only from an IP protocol, but from a soft IP, you can actually create design automation flows around this, such as you can quickly iterate and develop chiplets with much fewer resources than you otherwise would have. So we refer to this internally as kind of our SoC design cockpit. It's a guided SoC cockpit. It's the easy button. You see the easy button. Nothing's ever that easy, but I'll talk about kind of what we're doing internally. But really, the ability to provide customers. Our goal really at Cadence is we're not a quote silicon product company, but it's really to enable this world of chiplets and where we're going, and to enable our customers to actually get to market much faster than they otherwise would have. And really, to do that in a way, it's bringing EDA, hardware, and IP kind of all together in such a way that they can actually design and do this with a fraction of the resources than they otherwise would have, and allow them to focus just on the things that differentiate them and not have to worry about everything else. So, the group that I'm in is called the Silicon Solutions Group, so we kind of tend to think about this in layers. So at its foundation, certainly you have interface IP, you have processor IP, and as you want to go into kind of this chiplet space and to help companies, fundamental to this, and I don't have it here, but I can talk about it now, that we just acquired a company called Secure IC, which is an amazing end-to-end, world-class security solution, but you can't, for us, you can't go into this space unless you have that. So it's important that you have all of the pieces that you need to make this vision a reality, but certainly at the IP needs to be foundational if you're going to help companies. And really more and more companies come now and say, hey, especially as we get into chiplets, we need help with much more than IP. So building software and system IP level capabilities that layer on top of that, and then even all the way up into SoC and kind of chiplet architectures and reference platforms and designs that will help them. So really those layers of abstraction and kind of, you almost now need to take advantage of all of these resources to be able to deliver full kind of end-to-end solutions. So we no longer, when we think about IP, we no longer think of just put IP on a, on a test harness and tape it in. Everything we do now is designed in a chiplet framework. So all of our IP is kind of functions together in a modern chiplet. This helps us with kind of all of the design challenges that all of our customers. It gives us a way to kind of benchmark all of the automation flows that we're trying to develop along the way. Do we really see a 2x gain, a 3x gain, a 4x gain? So this is, for us, when we talk about one small step for SSG, but it's one giant step for Cadence, is bringing together the power of EDA, IP, and hardware all together, and even software to help customers. And this should be known, and I think I haven't been here at this conference. I just got in late last night, but I'm sure you've talked about a lot of the design challenges. If you go back, and I try to put this kind of over time, you went from worrying mostly just about functional to, as you get into a chiplet world where you have chiplets next to each other, with street distances of, a few millimeters to down, tens of microns, potentially thermal mechanical issues, become first order design problems. It's no longer just functional timing, traditional PDT worries, no longer just traditional kind of functional worries. So how, a chiplet world is very exciting, but the number of design challenges that now become what I call first order design challenges increase. And so the value and importance of end-to-end flows that are solving and optimizing for all of these, as opposed to just treating all of these in kind of a serial nature, becomes far more important. And so for us, our focus on helping customers win, say in the ARM chiplets ecosystem, and I say this, most designs when we look at out there are ARM-based design systems. We believe, the collaboration with the industry, ARM with their CSA and CSS architectures is very, very important. Relationship with all of the standards bodies. We can talk about UCIe or other various forms of potential die-to-die solutions, but it's very important to have strong relationships with all the standards bodies, be active, and then bringing together kind of the implementation capabilities that we have. And then really building on, as I say, our very rich heritage of design automation. So for me, again, one of the exciting things is really, coming from a world of product and design into kind of feeling like, hey, the ability to actually marry all of these capabilities and do it with a lens of products, and especially in a world which is now being shaped increasingly by chiplets going forward, is very important. So this end-to-end approach, if you really want to help reduce the number of interfaces that companies have to deal with such they can get to market faster, is really key to put these all together in a coherent strategy to help customers. So, from the production-proven IP to the system-level expertise to the experienced integration teams to a seasoned operation team, I call this kind of from an IP to wafers mindset to help companies. Anyway, so it's interesting, and I'll say kind of in the last thing, I think there's several phases. In this, monolithic was kind of one phase, and I think companies, as they started to deal with the cost crisis, I think internally we're looking at their architectures, and disaggregation became a solution. And then eventually, as the example I showed, they began to realize the agility, the power performance, the R&D, the segmentation advantages. This became really an opportunity for them to actually be far more productive. And I think now what you'll see, again, going forward in kind of the end state, is you see now many companies wanting to get into the custom silicon business, and also there's the geopolitical. I think it was very interesting, with NVIDIA, not being able to sell more than 50,000 GPUs to non-favored nations. That's been a wake-up call, I think, for many countries on how do they manage from a global supply assurance standpoint. Many companies which have very successful architectures, when they go to companies, well, hey, they would love that, but the issue of dark silicon, they want to be able to add their accelerator. So how do you do this? And chiplets is certainly one very powerful solution on how you're able to kind of meet your customers' needs. And I think, also from a geopolitical standpoint, we'll see this will become far more important. And then you'll even see, I think, in the end state, how foundries from a heterogeneous, I think a lot of people get concerned, well, chiplets from different foundries, will those all work well together? And I think you'll see the evolving of, say, kind of the software and EDA tools landscape to be kind of multi-PDK, especially as bump pitches and packaging technology gets down. You will, in the end state, you'll get down to where you have a canvas where you can design across multiple process nodes, and really outside of, within the package, the ability to manage electricals will become almost like designing monolithic again.